Hello and welcome everyone. Welcome to this ARSET training on assessing the impacts of fires on watershed health. Part 1 is going to be on satellite observations and tools for fire risk. My name is Amita Mehta and I will be conducting this session with the help of my colleague Sean McCartney. We'll start with a brief introduction to ARSET. ARSET, or Applied Remote Sensing Training Program, is NASA Applied Sciences capacity building program, and it provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools. ARSET trainings include a variety of applications of satellite data on these thematic areas such as agriculture, climate and resilience, disasters, ecological conservation, health and air quality, and water resources. These trainings are tailored to audiences with a variety of experience levels. ARSET trainings can be online or in-person trainings are also designed and provided sometimes. They are live and instructor-led, such as this one, or there are also asynchronous and self-paced training available on ARSET website. The link is provided here. These are cost-free, as I mentioned before. Most trainings are bilingual in English and Spanish, or sometimes they are multilingual with additional language such as French. Even if the trainings are not bilingual, the material is available in English and Spanish, both languages. ARSET trainings, they use open source software and data and accommodate different level of expertise in remote sensing. So we'll start with today's session. The training is about assessing the impacts of fires on watershed health, and we'll start with an overview first. So overall training learning objectives are given here. By the end of this training, participants will be able to analyze the key fire science criteria to select the appropriate data from satellites or instruments for a given watershed, distinguish, compare, and contrast the biophysical conditions pre- and post-fire, acquire land use and land cover maps for the region of interest, select river basin and sub-basin boundaries for their region of interest, recognize how to apply the soil and water assessment tool, a river basin scale model, to simulate the quality and quantity of surface water and groundwater. This is basically for post-fire application. There are several prerequisites here for better understanding of the material presented in this training. There is fundamentals of remote sensing, satellite observations and tools for fire risk detection and analysis, using Google Earth Engine for land monitoring applications, and Texas A&M instructional videos for SWOT that we will be doing this in this training. There will be 3 parts to this training. Today, part 1 will be on satellite observations and tools for pre-fire risk mapping. Second part will be on Earth observations and using Earth observations in SWOT model for assessing post-fire water quality in watersheds. And the final part will be on using Google Earth Engine to monitor post-fire impacts. There will be one homework posted on ARSET website on the last day of the training, and that will be due on 27th of July. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignments before the given due date. Also, please note that part 1 and part 3 will have hands-on exercises using Google Earth Engine, in which you will be able to do pre-fire risk mapping as well as do post-fire impacts assessment. There are several types of fires that we observe: wildfire or wildland fire, deforestation, agricultural, and peat fires. They burn different types of vegetation, such as wildfire burns forests, shrub, grasses, deforestation clears forests, agricultural fire burns crops, grasses, and shrubs. Peat is a soil-like material that burns with low intensity and it smolders. All these fires, they have seasonality, especially wildfires and peatland fires. They occur mostly in dry seasons and they vary from year to year. There are natural as well as human-induced causes for fires. For wildfire, a natural source is lightning, and winds can also then exacerbate once the fire starts. Humans can cause fires by prescribed burning. Either accidental fires can start, or that could be arson. Deforestation and agricultural fires are completely human-made. One is for clearing forests, one that burns crops to clear fields. Peat fire can be natural or human-induced. Wildland fires and deforestation fires can have very high intensity and can burn millions of acres if they're not controlled. Agricultural and peat fires are low intensity. Actually, peat fires can be underground and they are difficult to put out. So fires are unique phenomena in the sense that they interact with all Earth system components or spheres, as we call them, lithosphere, biosphere, atmosphere, and hydrosphere. Fires are generally caused by dry and warm conditions in atmosphere, hydrosphere, and lithosphere, and then they impact back also to them by affecting air quality, by putting smoke and particles in the atmosphere. They add greenhouse gases such as carbon dioxide and carbon monoxide. They alter energy budget by scattering and absorbing solar radiation, and also impact cloud physics. Once fires occur, they burn vegetation and make soil bare, and then they alter soil composition, both chemical and biological. And once fires occur, post-fire rain can trigger more erosion, more flooding, and landslides. Also, they impact downstream water quality. Once more erosion is there and more flooding is there, from bare soil, more nutrients and sediments, they wash into reservoirs and streams where the fires occur. Most importantly, fires affect all lives. They have health impacts and economic impacts, as we know. So in this training, we will focus on wildfires. As we just talked about, they impact human lives, infrastructure, ecosystems, and wildlife. You can see here in this plot, this is for North America. So different Caribbean, Central American countries, US and Canada are shown here from GWIS. What it shows is the ratio of number of fires in each country with respect to area of that country. So impact of fires depends on how many fires as well as how much area is affected. So the big one here is Montserrat, then US is down here, this is Canada, Guatemala and Honduras are shown here. So fire impacts can vary based on where they occur and in how many numbers they occur. For US alone, the 10 years average cost of fire suppression is more than $2 trillion. While many wildfires are caused by humans, climate change is expected to increase wildfire activities due to warmer and drier conditions. Frequency, intensity, and extent of fires vary interannually depending on a complex connection between weather and climate conditions and ecosystem processes. The top chart here shows annual wildfires, so numbers in thousands here, and acres burned in millions of acres. This is for the US between 1993 and 2020. 2022. So clearly you can see that the number of fires vary interannually, and how much area is burned, how acres are burned is also interannually, they vary strongly. Here you can see a slight upward trend on top of that interannual variability for how much area is burned by fire. So in this session, we are going to focus on fire risk mapping. Fire risk mapping is the probability that a fire might start in a certain area. So risk is determined by compiling relevant factors that influence fire ignition and behavior. To calculate fire risk map, or to have estimation of that, there are three aspects to that. First, the probability of ignition. Second, the biophysical influences on fire, such as fuel load, moisture content, flammability of vegetation, and topography. And finally, the spread of fire once it gets started. As you can see, all these factors have to be known for fire risk mapping, and that's why a comprehensive fire risk map is usually a challenge. In this training, we will try to do that by focusing on monitoring fire fuel, temperature, precipitation, and soil moisture in a given watershed. So as you can see, this star marked in here, these are all the observations required for fire risk mapping. In situ measurements are sometimes not adequate, and so remote sensing observations are used. Also, Earth system models are used for these parameters. The stars, they indicate parameters that are available from remote sensing. And so that brings us to today's topic, that is an overview of satellite observations and tools for fire risk mapping. Objectives for today are as follows. We'll provide examples of fire science criteria, specifically for pre-fire conditions, and learn how to select appropriate data from satellites for a watershed of interest. There will be a demonstration of how to delineate river basins and subbasins for a watershed of interest. And finally, we will learn to calculate anomalies in biophysical and meteorological conditions for a watershed of interest. And we will do that by using Google Earth Engine. Here is the outline for today. We'll have an overview of our Earth observations for fire risk assessment. Also, overview of tools for monitoring fire risk. Remote sensing based fire risk indicators. And then we will look at a couple of case studies, recent fires in US and Canada. We will have demonstration by Sean McCartney. He will be showing pre-fire risk assessment for two case studies, Wolsey fire in California and recent Quebec fires. And he will use Google Earth Engine to demonstrate fire risk assessment. Specifically, he will demonstrate how to delineate a watershed, derive standardized precipitation index or SPI, that is to assess dry conditions, and monitor anomalies, which is departure from long-term mean values for soil moisture and normalized difference vegetation index within a watershed. Just a note here on how to ask questions. So please put your questions in the question box and we will address them at the end of the webinar. Feel free to enter your questions as we go, and we will try to get to all the questions during the question answer sessions after the webinar. The remainder of the questions which we cannot address during this time will be answered in the question and answer document, which will be posted to the training website about a week after the training. We will start with an overview of Earth observing satellites and sensors for fire risk assessment. Just a quick review here that most fires occur in dry and warm conditions. Both weather and climate conditions impact fire risk, and vegetation cover, type, density, and height, they provide fuel for fires. So we are going to map some of these to get fire risk assessment. An example is shown here for annual fire weather days, and that's based on average annual hot, dry, and windy days between 1973 and 2022. So here you can see that the red area shown where the annual fire weather days are larger. And so wherever these conditions are met, there is likelihood of fire. Watershed data relevant for fire risk assessment are listed here, including precipitation, surface temperatures, soil moisture, vegetation fuel, topography, humidity, and winds. All these data are available from remote sensing and Earth system models from NASA, and they can be used for pre-fire risk assessment, also for during fire and post-fire watershed conditions assessment. In the next few minutes, we are going to have an overview of how to get these data from which satellite sensors and which models. More details about these satellites and models can be found at this prerequisite webinar. We will start with a couple of tables summarizing satellites, sensors, and models that provide watershed data for fire risk assessment. We will have a quick overview of these satellites and models, but these tables provide a nice summary of all the data sets and their sources. So you can see parameters in this column: satellite, sensors, and spatial and temporal resolution and coverage. All the acronyms are defined here in the bottom. Precipitation is available from combined TRMM and GPM satellites, and also with multiple satellites from International Satellite Constellation. Sensors are microwave radar and radiometers, and international satellites also have microwave emitters and sounders. Spatial resolution for precipitation data is 1/10 of a degree, or about 10 kilometers. It's out there available at every half hour, daily, and monthly time scale, beginning from June 2000, which is combined TRMM and GPM data record. Soil moisture is available from SMAP, which carries L-band microwave radiometer, and the data are available at 9 kilometer and 36 kilometer resolution on daily basis, starting from early 2015. Topography is available from Shuttle Radar Topography Mission carrying C-band radar, which flew on a space shuttle in 2001, and the digital elevation data are available at 30-meter resolution. Land cover, land surface temperatures, and vegetation indices such as NDVI can be obtained from these satellites and sensors. So Landsat, Terra and Aqua, Sentinel-2, which is a European Space Agency satellite, SNPP and JPSS, these are NOAA polar orbiting satellites, and these are the sensors. Landsat has been the longest flying mission. A series of Landsat satellites were launched between 1972 to present. They have optical and thermal infrared sensors. The resolution of Landsat is 30 meter, and data are available every 16 days. Terra and Aqua, SNPP, JPSS, so MODIS and WIRS sensors, they are similar. Both have optical, so visible infrared, near infrared to thermal infrared bands are available in these sensors. And as you can see, spatial resolution varies. From MODIS, it is 250 meter to 1 kilometer, and WIRS, it is 375 meters to 750 meters. Both MODIS and WIRS, they provide near daily measurements, and then they are used to get other measurements such as 8-day and monthly. MODIS, so from Terra and Aqua, that is the second longest time series after Landsat, so it's available from 2000 to present. SNPP and JPSS, so WIRS data are available from 2012 to present. MSI is the most recent one from June 2015 to present, but it has the highest spatial resolution among all, 10 meter, 20 meter, and 60 meter depending on the bands, and temporal resolution also is 2 to 5 days. Next, here we have a satellite observation-based model for fire risk assessment. So MERA-2 is a modern era retrospective analysis for research and applications, and that provides fire weather and climate data, including precipitation, surface temperature, relative humidity, and winds. These data are available since 1980 at hourly and monthly temporal resolution, and the spatial resolution is half a degree by 0.667 degree. Additionally, there are land data assimilation models. This is for North American land data assimilation system, and this is global land data assimilation system. They provide soil moisture and evapotranspiration. NLDAS has 1/8 of a degree resolution and available since 1979, hourly and monthly temporal resolution. GLDAS is available at 1/4 degree and 1 degree resolution. It's a 3 hourly and monthly temporal resolution. These data are available from 2000 to present. So this summarizes watershed data that you can obtain from different satellites and models depending on your watershed, depending on the time period that you are interested in. You can choose a data set to work with. Now we're going to go through very quickly to see some features of the satellites and models that we just saw. So GPM core satellite is in a low inclination orbit, and it was launched on February 27, 2014. It covers 65 south to 65 north. Its predecessor, TRIM, covered tropics between 35 south and 35 north, but both TRIM and GPM, TRIM was launched in 1997, so combined TRIM and GPM, they provide long-term precipitation, so that's what we're going to use in this training. And sensors, as we saw earlier, it's a microwave radar and imager. A special note about this iMerge data. This is combined TRIM and GPM data. There are several versions with different latency. So early and late, therefore 4-hour and 14-hour latency, which are quite useful for looking at weather conditions pre-fire and post-fire also. The final product is a research product which has 3 months latency. So we are going to use iMerge data. These data are available from Google Earth Engine. And so we will look at that to look at dry and wet conditions in pre-fire seasons. So here, something to note is that it's not just TRIM and GPM, but international constellational satellites being used. So they all have microwave sounder or imager, which are calibrated with TRIM and GPM data. And as a result, half-hourly 1/10 of a degree precipitation can be obtained from this constellation of data, constellation of satellites. Next is soil moisture active passive. That is also a polar orbiting satellites providing global soil moisture. And that's a L-band radiometer, as we saw earlier. Landsat and Sentinel-2. They are specifically used for vegetation-based fire applications, among other things. And we already talked about their temporal and spatial resolutions. But here, vegetation extent and type, vegetation stage and health through different indices, and vegetation moisture index. So these can be obtained from Landsat and Sentinel-2 datasets. MODIS has been used for NDVI. This is Enhanced Vegetation Index, High Temporal Resolution Phenology, and so land cover classification based on MODIS is available for a long time. We already talked about spatial and temporal resolution. So this is just to give an idea of how NDVI shown here looks like over Africa from MODIS. Similarly, VIRS, which is flying on NOAA polar orbiting satellites, that also provides vegetation-based fire applications. So vegetation stages can be obtained from VIRS, just like that they are obtained from MODIS, vegetation health, and temperature, and vegetation health index. They're all available from VIRS. And again, we have already talked about spatial and temporal resolution and coverage. MERA2, it's a atmospheric model that blends the vast quantities of observational data with output data from Goddard Earth Observing System, or GEOS-5 model. So here, from 1980 onwards, all the available observations which are assimilated in MERA2 are shown in here. So these are number of counts in 10 to the 6, so many millions. So conventional data earlier, and then as we go past about 2002 or so, you can see that multiple satellite sensors, they have been added in assimilation. It provides state-of-the-art global analysis for weather and climate, and also it provides improved hydrologic cycle. Both GLDAS and NLDAS that we talked about are water and energy balance model with assimilation of remote sensing data. Basically, land surface model, they're forced with inputs such as rainfall. In this case, it's stream-based multi-satellite data, meteorological data from global reanalysis, vegetation mask, land water mask, leaf area index from MODIS, and clouds and snow from NOAA and Defense Meteorological Satellite Program, and provides integrated output of soil moisture, evapotranspiration, runoff, and snow water equivalent. Both soil moisture, evapotranspiration can help look at dry conditions or drought conditions which are conducive for fires. NLDAS, there are 4 different land surface models, different versions are there. Basically, similar inputs, but here precipitation is provided from rain gauge data. This is just for North America, and meteorological data from NOAA North American Regional Analysis, and similar integrated output can be obtained just as in GLDAS. NLDAS is part of this land information system based system that provides all this integrated output for North America. So that concludes our information about satellites and models and how to get, where to get watershed parameters for fire risk assessment. Before we actually start looking at some of the data, let's look at remote sensing based tools for monitoring fire risk. These are already online available tools which use some of these satellite data and in situ data. So that is just for your information. And again, you can see more details in the prerequisite webinar shown here, or link is provided here. So there is land fire, that is existing vegetation cover and height. It provides topography, fuel, and fire regime in the US. All these are fire risk monitoring tools for US and regional fire monitoring. North American Wildland Fuel Database, or NAWFD, that's per hectare fuel load from field data, that is for US. The Forest Inventory and Analysis, or FIA, is the US Forest Service portal for field-based and remote sensing-based information about tree species, size, health, and mortality. This also is for US alone. Firecast, it's a remote sensing-based near real-time fires and forest disturbance alert system. This is limited to US and specific countries in South America, Indonesia, and Madagascar. So here there is an example shown from Firecast about the Woolsey fire that we are going to talk about later. This is just for your reference so that you can look at some of these tools for your information. There are also global tools. One is Evaporative Stress Index Mapper, and that provides evapotranspiration anomalies as an indicator of dry conditions. Then there is Global Wildfire Information System, or GWIS, that provides a comprehensive view and evaluation of fire regimes and long-term fire weather forecast and fire effects at the global scale. And here, GWIS is shown, so you can see this recent fire in Nova Scotia in early June, and fire weather index from GWIS is also shown in the bottom panel. So we reviewed the fire monitoring tools, but in this training, we are using these general utility tools. First is Google Earth Engine. We will use this to analyze satellite data we just introduced, and that is to actually do fire risk mapping. In next session, we will talk about soil and water assessment tool, a modeling tool developed by Texas A&M University. And NASA Access, this is a R-based code system that allows satellite data extraction that can be used as input for SWOT. So both SWOT and NASA Access we'll talk about in next session. So what are some of the remote sensing based indicators for monitoring fire risk? And here is the list: Standardized Precipitation Index, or SPI, Normalized Difference Vegetation Index, Enhanced Vegetation Index, Soil Adjusted Vegetation Index, Normalized Difference Water Index, Normalized Dry Matter Index, Evaporative Stress Index, and anomalies of precipitation, soil moisture, and vegetation indices. All these fire risk indicators can be calculated from the datasets that we talked about earlier for Watershed. More details can also be found at this link. There are additional fire risk factors, such as vegetation height and density, elevation that impacts rainfall, temperature, type of vegetation, wind exposure, potential for lightning strikes, and terrain aspect and slope, which impact amount of solar radiation and potential for fire spread. In this training, we're going to look at case studies for which we will have fire risk indicators. We're going to focus on these three. So one is Standardized Precipitation Index, Normalized Difference Vegetation Index, and then anomalies of land surface temperature, precipitation, soil moisture, and NTVI. Just a brief introduction to SPI. So SPI is primarily defined to characterize meteorological drought or dry condition. Mathematically, historical rainfall data at any location fitted with gamma distribution represent cumulative probability function. And if a rainfall event has a low probability on the cumulative probability function, it is indicative of a drought event. The SPI values can be interpreted as the number of standard deviations by which the observed rainfall anomaly deviates from the long-term mean, and it is calculated as shown here, where P is actual precipitation, P star is the mean precipitation, and sigma P is the standard deviation. So it just tells you how dry or wet conditions are based on precipitation compared to climatology. Normalized Difference Vegetation Index, it's widely used as a metric for vegetation health and phenology, and it's a measure of vegetation greenness. It ranges from -1 to 1. Negative values to 0 means there are no green leaves present. Values closer to 1 indicate the highest possible density of green leaves. And it is derived based on near-infrared and red spectral reflectance ratios as shown here. You can see here, this is the Woolsey fire case. Again, the NDVI can be seen. In this, you can see a lot of brown area where there is negative NDVI. This brings us to the case studies we are going to work with today, and that's recent fires in US and Canada. The first case study that we're going to focus on, and Sean is going to demonstrate, is Woolsey Fire. This fire started on November 8, 2018 in the Woolsey Canyon near Los Angeles and Ventura counties in Southern California. The fire burned almost 100,000 acres of land, and there was an estimated of $6 billion damage to infrastructure because of the fire. The fire started when power lines arced, igniting dry grasses in Woolsey Canyon, and was spread rapidly by strong Santa Ana winds, which usually blow in Southern California. It's part of their climate system. The second case that we are looking at is fires in Quebec in 2023. In Canada this year, overall 3.3 million hectares land has been burned due to fires. But the fires that we are talking about, they occurred in early June, worst in Quebec, with about 160 fires and 100,000 people displaced. Here you can see a snapshot from NASA Worldview showing these red areas are the areas where there are fires from Podest and Weirs, and this was taken on June 6th of this year. And you can see multiple fires in this area. A storm system off the coast of Nova Scotia forced smoke from this fire south into the US, and for several days it was quite smoky all the way down to here in Washington area as well. So here's an example of how Earth observation can help us see fire risk. So this snapshot is shown from MERA-2, surface skin temperature anomalies. That's departure from long-term mean between 2001 and 2022. And you can see that this area was much warmer than normal for month of June. Month of May, this is like pre-fire, when the fire occurred, it's early June. Similarly, I-merge precipitation anomalies for May of 2023, it shows almost everywhere it was below normal. So it was pretty dry and warm, and this shows dry and warm anomalies indicating fire risk. So these are the areas where you do see a lot of fires occurring in Canada. So this is one way to look at Earth observations and quickly see anomalies to identify areas of risk for fire. So now we will have demonstration of these pre-fire risk assessment using GEE. Before I hand it over to Sean for demonstration, here's the introduction to Google Earth Engine. For those of you who are new or you have not used, GEE takes advantage of cloud computing capabilities to provide users with a single place for accessing satellite data, applying remote sensing methodologies, and displaying analysis results. So you can have data, you can have your own algorithm, and then you can apply results to your area. GEE's Application Programming Interface, or API, allows users to easily apply land cover monitoring algorithms and other algorithms and classifications with coded commands. So it's a versatile tool, and a lot of information can be found. There are online tutorials, there are ready-made codes that are available online. It's a cloud-based raster computing, and that removes barriers and limitations related to data hosting and storage, imagery access and availability, and personal computing capabilities. That means you don't really have to download data. You just go to this cloud-based tool and do raster computing right on this site and visualize it. You can upload your own shape files, you can upload your own data as well, and do processing without downloading large amount of data. So it's a central repository for a lot of data as well. And GEE is free for scientists, researchers, and developers. However, you have to register with Google Earth Engine and you have to have a username and password to use it. Generally, there is application programming interface that is used to program and work with GEE. The Earth Engine JavaScript API is currently the most widely used method of working with GEE. But there is also a Python API through Google Collaboratory or Colab that can be used if you are interested in using Python. A little bit of work is required for that. JavaScript API is quite common and it's very widely used as mentioned here. So uses of GEE for satellite imagery analysis includes automation of data processing and display, near real-time monitoring. It's limited to availability of data in the catalog. Not all datasets are available in near real-time, but many are. Machine learning algorithm applications are available. Graphical user interface implementation is there. So there are several functionality that are very useful for satellite imagery analysis in GEE. So with that introduction, I'm going to hand it over to Sean McCartney. He's going to use GEE and walk us through how to access some of the satellite data that we introduced earlier and how to calculate SPI and anomalies to look at pre-fire risk mapping. So Sean, Victor.
Thank you, Amita. The following case study will demonstrate how to calculate the standardized precipitation index, soil moisture and vegetation anomalies, and demonstrate how to delineate river basins and subbasins for a watershed of interest. As Amita mentioned earlier, the standardized precipitation index, or SPI, is a z-score deviation from the mean in units of standard deviation calculated from the CHIRP's precipitation values for each pixel location during a given reference period. The script we're using today was adapted from the United Nations drought monitoring using the standardized precipitation index. We've included a link to that in the commented section at the top of the script. Monthly SPI will be calculated based on daily CHIRPS data since 1981, which will be summed to monthly precipitation data for our analysis. As precipitation is usually not normally distributed, a gamma probability function is commonly used, but is not supported in the script. The resulting SPI values are therefore used as an estimator. The first step in this process is defining our area of interest, or AOI. To do so, we use the polygon tool in the top left corner of the map pane to draw a bounding box around our study area. So to do so, we're going to go ahead and create a new layer, and we're going to use the draw a rectangle geometry, and we're going to go ahead and draw, in this case, this is just as a reference. I've already created a bounding box or an area of interest, but this is just to walk you through the steps so that you see it for yourself. So after we've created that bounding box, we're then going to go to the gear wheel, and we're going to rename the bounding box that we just created, and we're going to rename it AOI, which stands for area of interest. Then under the name, you can see that there is a import as option. It's very important that we change this from geometry to feature collection. And those are the steps involved in creating our area of interest. I'm going to delete this because I've actually already created an area of interest already. I just wanted to walk you through the steps so that you could see it for yourself. If we scroll down in the code a little bit further, now that we have our area of interest defined, we can see that in lines 48 and 49, we will be setting the base map to be satellite view, and we will also center the map window on the defined area of interest, or AOI, as well as establishing the zoom level. In this case, we've set the map center at the AOI, and we've used 6 as the zoom level. You might need to change this parameter for the zoom level most appropriate for your area of interest when you're doing this calculation. The next step, skipping down, is to set the time frame for our analysis. In line 58, we create a variable named first image to obtain the first chirps daily data from the time series. And again, that first image is from 1981. Since the data are indexed, we used 0 to get the first image in the time series. Line 59 defines a new variable latest image and assigns an Earth image date of June 1st, 2023. Since chirps data have a spatial resolution of 0.05 degrees, which corresponds to approximately 5,550 meters at the equator, we define a variable resolution and assign the value 5,550 meters as the spatial resolution of our chirps data. The next section of code that I'm highlighting here, from lines roughly 72 to 85, sets the time scale of our analysis for SPI. Meteorologists usually recognize 1 month as the shortest time scale for the calculation of SPI. Shorter time scales might underlie random fluctuations in precipitation, so it's always good to choose 1 month or greater when calculating SPI. SPI can also be calculated for longer time scales than 1 month, like 3 months, 6 months, 12 months, or even 24 months. The following settings will give you the possibility to set your own time frame for the calculation of SPI. It is important to note that for this code, SPI calculations only work for the following quantity of months. And for those quantity of months, I'm highlighting them right here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24, and 48. For example, 18, which corresponds to a year and a half, would not work. So it's good to use only the months that are provided here highlighted for your analysis of SPI. Line 84 defines a variable named time step, where we select the value 2 as the number of months for our analysis. Setting the time step to 3 would calculate SPI for 3 months. Setting the time step to 6 would calculate SPI for 6 months, etc. But again, we're just going to use the value 2 because we want to calculate the standardized precipitation index for 2 months, the 2 months leading up to June of 2023. This next line of code in line 91 just basically says that we want interactive chart to show, and we're setting that to true. Then, starting at line 97, we're defining a variable which we're naming threshold months, and we're going to set that threshold at 12, coinciding with 1 year. And then in line 100, we're defining a variable named time diff, and we're creating a list with a lag of 1 month between each list entry, starting from the latest image, counting backwards. In line 103, we're defining a variable named list, and we're creating a simple list indexed from 0 sequentially to the variable defined above. Then from lines 106 to 112, what we're doing is we're defining a variable named timelistDate to map the dates beginning with the latest image of the month's ends over the list, counting backward in time. We're then printing the dates from the list to the console tab. And we can see that here. If we go to the console tab, which I'm circling on the right of the screen, the top right of the screen, we can see that we have a list here, 255 elements. And we can see that starting from June of 2023, and each time step is going back in time from the index of 0. We're going back 2 months, and we're going back from the most recent, which is June of 2023, and we're going all the way back to the very first chirps image, which is from February of 1981. So what we're doing in that block of code that we just ran was basically printing the list of dates to the console tab. Then in line 115, we're defining a variable sorted time list to sort the list above according to their dates. Then this next big chunk of code here, roughly from lines 118 to lines 140, we're defining a variable precipitation sum, and we're mapping a function calculating the monthly sum of chirps. Just those images will be kept whose time frame corresponds to the user-provided number of months. In line 144, we're defining another variable named summed chirps collection, and we're copying the properties of the chirps collection to the monthly collection. And then in this big chunk of code here, from line 149 to line 203, what we're doing here is we're determining the approach to calculate SPI based on the number of months. If the number of months is less than 12 months, the day of year information has to be used to find the correct images. If SPI is calculated for 12 or more months, the day of year information is not necessary. Depending on your approach, if you're calculating SPI for 2 or 3 or 6 or even up to 12, then again, you'll be using a different approach. And after at the bottom of each of these calculations, SPI is being performed to subtract the mean precipitation from the selected month with the result divided by the standard deviation to make that calculation. And that's what this big block of code is doing. So depending on the time step that you're using, a different algorithm will be used. And then from lines 207 to 215, we're using a print statement for the time period of the analysis, and we're defining a variable SPI monthly viz, which we are using as visualization parameters. And finally, we're adding the SPI results as a layer to the map window using the naming convention provided in line 215. Since we selected June 1st, 2023 as the last image for the analysis, and the reason why we did this is because this was a peak time of the fires burning in Quebec, Canada. That's why we selected June 2023. We're going to be using 2 months as a time step for SPI calculation. And finally, the name of the layer will appear in the map window, and it will be using the naming convention that we're using in that last line, which will be SPI2 from April 2023. And then in this block of code here, from lines 220 to 243, we're defining variables to plot monthly precipitation across the time series of chirps data within the area of interest, then print those charts to the console tab. Lines 246 to 261 define variables to plot 2-month SPI values within our area of interest from the beginning of the chirps time series through June 2023. And if we go to the console tab on the right, we can actually see that when we run this code and we print these charts to the console window, we get the results. And if you want a larger image, you can go to this pop-out here, and it'll create a new tab with the chart in a new tab. And we can also do that for the SPI 2-month chart based on mean values within the area of interest as well. So there's just another way of charting out the results from our SPI analysis. And then from lines 266 to 313, we are creating an inspector chart for SPI values. The chart with SPI values will only appear when we use the inspector tab and click on a given pixel within the map window, which I will demonstrate after we've run the code. And then line 315, we print the list of dates for SPI2 to the console tab, and in line 317, we print the metadata of the chirps image collection coinciding with SPI2 to the console tab. And we can see that if we scroll down, again, we're on the right-hand side here, we see the console tab, and if we go down, we can see, sure enough, the list of dates for SPI2, and then also we can also see the chirps collection with SPI2, which has the metadata included within all of these. So it's just more way of viewing the results of the SPI from the chirps data. And lastly, from lines 322 to 329, we're creating a title for the map window, and we're going to set its position. So before I go any further, I'm going to go ahead and I'm going to click Run so we can actually see the results of what we've done so far. We can see that using our defined area of interest, very soon in the map window, we'll start to see the results of the 2-month standardized precipitation index, which is going back 2 months from June of 2023. And in the map window, anything in red or orange or yellow coincides to negative SPI values, and anything in green and blue are positive SPI values. And again, these are viewed as z-scores away from the mean. And if we use the inspector tab, which again, it's up here on the upper right, if we click on any of the values, I'm going to choose a value in red because these are negative SPI values, meaning there's a deficit of precipitation compared to the long-term mean. What we can see is based on the pixel that the long lat, which is given here, if we're looking at the inspector, we can also go down and we can see that the SPI value here is basically -2. It's negative 1.98. So just rounding up, that's a -2 value, which means that there is a strong deficit of precipitation compared to the long-term mean for that exact pixel. And in the code, we also embedded the ability to have for that specific pixel the SPI2 for that pixel. So that this was also a block of code that we included in our script. And again, we can pop that. We can plop this out using the pop-out window to go to another tab. So moving on in the script from SPI, now that we have established for the province of Quebec and for the surrounding provinces as well, the precipitation anomalies, we're now going to move on to the soil moisture anomalies. So moving on, we will now move to drought monitoring using the Soil Moisture Active Passive, or SMAP mission, which will help us to assess soil moisture anomalies within our area of interest. And to learn more about the SMAP Level 4 image collection, we can copy this file path, which we have right here, if you're interested in learning more about it. So what I'm going to do is I'm going to use Control-C, and then up at the search bar, I'm going to paste that, and we can see that it gives 2 options for data sets. What we're using here is this level 4 global 3-hourly 9-kilometer surface and root zone soil moisture. So if I click on that, we can learn more about the data set. And if we want to open this in a new tab and learn even more, we can use this pop out. So we can pop that out, and then this takes us to an Earth Engine page, which gives us a lot more information about description of the data set, the bands that are provided in this data set, as well as terms of use and citations. So these are all just nice, convenient features that we can have for learning more about the data if we're not familiar with the SMAP dataset. Next thing we're going to do in line 341, after we've defined that variable to for the image collection specific to that SMAP level 4, we're going to filter it based on the date, which is May 20th and May 21st. This is a 30-day window in which the anomaly will be assessed. So because we were interested in the beginning of June, we picked May 20th as the 30-day window in which to assess soil moisture anomalies. And moving down in line 344, we define a variable SMSA, which stands for soil moisture surface anomalies, to select a specific band within the image, the SMAP image collection, which corresponds to the soil moisture surface anomalies. And then moving down in line 347, we're defining a variable named image, and we're returning the first image from the filtered dates, and we're clipping it to our AOI, or area of interest. And then from lines 350 through 353, we're defining a variable to output a histogram of soil moisture anomaly values within our area of interest and use a print statement to output the histogram values to the console tab. So if we go back to the console tab here and we scroll down, we can see that this histogram is here, and we can actually use the pop-out window to create a new tab, and we can actually visualize the spread of soil moisture anomaly values within our area of interest. The histogram of soil moisture surface anomaly values will help us to determine the visualization parameters for when we want to add the soil surface soil moisture anomalies to the map window, which is viewing the, having gone through the histogram, I was able to use that to determine the min and max values for visualization. So in lines 356 to 360, all we're doing is defining a variable for the visualization parameters for the soil moisture anomalies. And then lastly, in line 363, we're going to add that as a map layer. And we can actually go down to the layers here, and we can see it's not turned on, but I can turn it on. And that would be the soil moisture anomaly for the May 20th, 2023. In this case, the bluer colors being positive soil moisture values for anomalies and red values being negative soil moisture values. So those would be negative anomalies for the area of interest. So now that we have mapped precipitation anomalies and soil moisture anomalies, the next block of code will deal with the vegetation anomalies using the surface reflectance data from the MODIS instrument. For those unfamiliar with the Normalized Difference Vegetation Index, or NDVI, this index is generated from the near-infrared and red bands using the equation provided in line 371. NDVI anomaly images are useful as a measure of drought and fire risk when compared to normal plant health. Positive NDVI values represent dense and greener plant vegetation compared to the long-term mean. Negative NDVI values represent less green vegetation, useful as a measure of drought when compared to normal plant health. Ooh. I'm sorry about this. I accidentally kicked the wrong thing. Perfect. So in line 381, we're defining a variable named point for a longitude and latitude in Quebec, Canada, where wildfires are blazing as of June 2023. This location will be used to chart a time series of NDVI anomalies at that longitude and latitude. So this just gives us one more way of drilling on down from not only from the entire area of interest, but also to a specific location. And this will be seen later in the scripts when we look at more of the charts. And in line 384, we're defining a variable NDVI for the Terra Modis Vegetation Indices 16-day global data set, which is a 250-meter spatial resolution. And if you're interested in learning more about this data set, again, you can just use a Control-C or copy, and we can go up to this search window, and the result comes up instantaneous. And when I click on it, we can learn a lot more about this data set if you're interested. And again, we can use this pop-out window to open up a new tab to be able to explore all the different bands like NDVI, EVI, solar zenith, etc. These are just different bands and bit masks that are used for this, as well as citations and descriptions. So all useful information and very just one click or two away if you're interested in learning more about the data. So in line 387, we're defining a variable named NDVI to select the NDVI band specifically from the image collection. And then in lines 389, we're creating a function to apply a scale factor to the NDVI image. The scale factor is necessary to normalize the values between -1 and 1. In line 396, we're defining a variable modis NDVI to map the scale factor to the entire image collection using the function that we just created above. And then in line 399 to 404, we're creating a function to convert the long-term mean value for each month of the calendar year. And then in lines 406 to 410, we are defining a start date for the NDVI time series, as well as defining the number of months in the NDVI time series from the start date to a defined end date. So it's really important that this end date, depending on the month of interest for your study period, that you determine what this end month will be, because that will help determine how the NDVI anomalies are calculated for your month of interest. So it's really important that you change this parameter for your study period. And moving on, from lines 413 to 417, what we're doing here is defining a variable to create a function to index the sequence of dates from March of 2000 to May of 2023, and then we're printing the results to the console tab. So if we go over to the console tab here again, we can click down here and we can see that yes, all these list of dates are in fact sequentially in order. And then moving right along, we can see that in lines 420 to 426, what we're doing is grouping the results by month and then reducing within groups by the mean. The result is an image collection with one image for each month. And lines 428 to 433 subtract the monthly mean from the long-term mean to calculate the NDVI anomaly. And then line 436, we're defining a variable to convert the image collection to a single image with many bands, and each band equating to 1 month within the time series. And then from lines 443 to 448, we're adding the NDVI layer to the map window, calling the band name of your choice. In this example, we are calling element 278, which is associated with May 2023. We're also setting the min and max NDVI values, and we're defining a palette to visualize the map and defining the layer name for the map window. And then in lines 451 to 459, we're defining a variable chart to chart a time series of NDVI anomaly based on the point variable, that long lat, longitude, latitude, that we already defined above based on that location. And lastly, we will use a print statement to print the chart to the console tab. So if we scroll down here, we can see that yes, here is the band mean across all the images, and we can pop this out again in a different tab. Just different ways of exploring the data. In this case, it will be for that location. Okay, so now that we've created our vegetation anomalies, we will move on to mapping our firm's active fire data. In lines 467 to 469, we define a variable for the Fire Information for Resource Management System, or FIRMS. This is an image collection of active fires that are burning, and we're going to select band T21, which is the brightness temperature of a fire pixel, using MODIS channels 21 and 22. And this brightness temperature is in Kelvin. We then filter the date of the FIRMS image collection to June 6th through June 7th, 2023, coinciding with the date of the active Quebec fires. Next, we define a variable in line 472 for the first image from the filter dates. And again, those filter dates are June 6th to June 7th, 2023. In lines 475 to 479, we define a variable for visualization parameters to display the firm's data in the map window. And lastly, in line 482, we add the firm's fire data to the map window using the visualization parameters defined above, as well as define the layer name for the active fire image to display in the map window. And again, if we go down to the layers, we can start clicking on these. So for firm's fire detection, we can turn this on, and we can see for the dates that we specified, June 6th and June 7th, where the active fires were burning. Let's give it a second. Here we go. We can actually see a lot of those fires are in this region right here. And if we turn on NDVI anomalies, we can also see that a lot of those fires are in fact in areas in red, which would be vegetation health, which is less green than the long-term average. So just different ways of visualizing the results. And moving right along, now that we have our active fire data for our case study, the last data set we will bring into the script is Hydroshed's basins. The next section of code acquires river subbasins using the Hydrosheds project initiated in 2006 by the World Wildlife Fund in the United States, with the goal to create free digital data layers in support of large-scale hydroecological research and applications worldwide. Hydrobasins is one of their products generated from the Shuttle Radar Topography Mission, or SRTM, and represents a series of vectorized polygon layers that depict sub-basin boundaries at a global scale. There are 12 hydrobasin levels corresponding to different levels of sub-basins. In this case study, we'll be using hydrobasins level 9 and 7, but again, for your study area, you might choose to use different sub-basin levels. But again, for this case study, we'll be using levels 9 and 7. So in line 497, we would define a variable for the hydrobasins level 9 feature collection. In lines 500 to 503, we define the visualization parameters. And in lines 506 to 509, we draw the visualization parameters to the hydrobasins level 9 feature collection and add the level 9 subbasins to the map window and define the layer name. So if we go down here, we can actually turn that on, and we will see that these are the level 9 subbasins. And then for starting in lines 512 to 524, we repeat the same process using hydrobasins level 7 data. And scrolling down almost to the end of the script here, in this commented section, for those wanting to export the SPI data or any other layer that we've created in this case study to your Google Drive, you can uncomment the block of code shown in lines 532 to 540. Uncommenting the code will allow you to export the image to your Google Drive, specifying the coordinate reference system. Now, this case study was specific to the Canadian fires burning in the province of Quebec in June of 2023. So again, what we were able to do is look at the standardized precipitation index from April of 2023 to June of 2023 for the area of interest that we defined. And then what we did is we also created soil moisture anomalies, and this was a 30-day window which was built around May 20th, 2023, so that we can assess the soil moisture anomalies within our area of interest. And we can see for a lot of the area that we are interested in, there are negative soil moisture anomaly values. And again, if we turn on the firm's fire detection data on top of these soil moisture anomalies, we should be able to see that, in fact, they do overlap in terms of where the fires are and where the soil moisture anomalies are. There we go. And then we can also turn on the, we can also calculated NDVI anomalies. These are vegetation anomalies for May of 2023. So we can see that just one more layer of assessing soil moisture, precipitation, vegetation health for fire risk. And then we also brought in level 7 hydrobasins, and we also brought in level 9 hydrobasin, which is, these are subbasins within our area of interest. And so this was for one case study, and we also showed how to export the images to your Google Drive if you wanted to bring them into a GIS and do further analysis. But quickly, what we're going to do is jump to a different, we're going to go to a different script that we've created. And I'm going to go ahead and run the script. And it's basically doing the same thing that we, the same steps, the same data sets, only in this case, we're using a different study area and a study period. We're going to be looking at the Woolsey fire in around Malibu in Southern California in the United States. And this fire took place in November of 2018. It ravaged the Santa Monica foothills, as well as the area just to the west of Los Angeles, the Los Angeles Basin, San Fernando Basin, and it heavily impacted the Malibu hills around the city of Malibu. And so what we're looking at here, again, if we pan out, for those that might be interested exactly where this is, we can see the southwestern part of the United States, and then specifically in the extreme southern part of California, we can see that this is the area of interest in which we are performing this analysis. And we're going through the same steps. First, we're going to create our area of interest. And again, we did that by using the Draw a Rectangle tool. And once we had our area of interest defined, we were able to start bringing in different data sets. In this case, this was the chirps data. We set the base map, we set the area of interest, and we also defined the zoom level. We set the first date in the range, which is the first image from chirps in 1981. And in this case, we set the latest image of November 2018, which is when, November 1st, which is when the fires were taking place that month of November. So we want to be able to assess the SPI for leading up to that month in terms of precipitation. Again, we set the spatial resolution. In this case, we're setting the SPI to 12 months. So instead of 2 months like the previous script, we're setting it to 12 months. And then we're going through all the same steps as we went through in the last script. Nothing has changed here in terms of how we're calculating the standardized precipitation index. Then we're going to add these different results to the console tab so that we can view them. In this case, this is the 12-month precipitation time series based on chirps. And where we can also see we're also creating charts of the SPI, and then we're also creating a list of dates so that we can index all of these different months that we're calculating. And next, we're going to add that layer, which we've already done in the map window, and then we can move on to creating the soil moisture anomalies, which we're doing here. We're using the same data set as before, only this time we're filtering the dates from October 20th to 21st. And again, this is a 30-day window of soil moisture anomalies. And we're going to clip those, the results to the area of interest, and then we can add them to the map window so that we can see what those soil moisture anomaly values were leading up to this devastating fire that took place, this Woolsey fire in November of 2018. Next thing we're going to do is we're going to calculate NDVI anomalies. So we're going to go through the same process before, only this time we're going to change the longitude and latitude. This is for an area of interest or a location of interest here in around the Woolsey fire. We're going to use the same data set as before, this MODIS vegetation indices, and then we're going to select the NDVI band out of the image collection, and then we're going to calculate the anomalies, and we're going to add the anomalies to the map window, which we can visualize here. And then next, we're going to look at the firm's active fire data. So we're going to filter the firm's collection to November 9th through November 10th. And that is the day when the fires were raging in the Malibu foothills. We're going to select the band from the firm's image collection. We're going to establish visualization parameters. And then we're going to add the map layer to the map window, giving it a defined name, which in this case is firm's fire detection on November 9th, 2018. And we can see that, yes, a lot of the fires were burning in these foothills just outside of the city of Malibu in Southern California. And next, we're going to add the hydrosheds basins so that we can visualize where the fires were burning in terms of which subbasin. And again, we're going to use hydrobasins level 9 and level 7, and we'll be able to add those to the map window as well so that we can see where exactly these fires were burning in reference to these different subbasins. And then lastly, we're going to provide the opportunity, if so chosen, to be able to export the data to your Google Drive. So this concludes the case study demonstrations for both the Quebec fires in Canada from June of 2023, as well as the soil moisture, vegetation, precipitation anomalies, as well as active fires and subbasins for the Woolsey fire, which took place in November of 2018. So I want to hand it back to Amita to wrap things up, and I want to thank you all for your patience. And Amita, back over to you.
Thank you for the great demonstration, Sean. This concludes today's session. So here's a brief summary of what we saw today. We introduced remote sensing satellites and sensors relevant to fire risk assessments. reviewed important indicators for assessing fire risk and remote sensing based tools for analyzing them, selected appropriate data from satellites for a watershed of interest, introduced examples of pre-fire criteria for fire risk in watersheds. We used GEE to demonstrate how to delineate river basins and subbasins for a watershed of interest. And finally, we saw how to use GEE to calculate anomalies in biophysical and meteorological conditions for a watershed of interest. You will have chance to work with GEE and replicate some of the codes that Sean demonstrated. Looking ahead to part 2, next week we will have Ibrahim Muhammad and Mehta Lopez giving information about SWOT. So we'll get familiar with how to run the soil and water assessment tool model by ingesting remote sensing data to predict the post-fire impact on sediment in a watershed. Here's just a reminder about homework and certificates. There will be one homework assignment that will be posted on July 13th on the ARSET website. Answers must be submitted via Google Forms, and the due date for homework is 27th of July. Parts 1 and 3 will include hands-on exercises to assess pre-fire risk and post-fire impact on a watershed using Google Earth Engine. You will be instructed to submit results of these exercises to our Google Drive folder by July 27th. Those of you who attend all 3 live webinars, complete the homework assignment by the deadline, you will receive certificate of completion approximately 2 months after completion of the course. Here's our contact information, ARSET website, follow us on Twitter, and here are our sister programs. Please check them out. So now we will switch to question and answer session. So please put your questions in the question box and we will address them in the order that they are received. Thank you. We have received a few questions here. Okay, I'm going to read the question. If we perform special resampling, can we use all the bands of Sentinel-2A for analysis? Yes, you can. You can resample the data. And GEE would allow, you can do that on GEE. So this is a common process performed on remote sensing bands to normalize and the spatial resolution of imagery. You have to be aware that the information in a given pixel can change when you resample from one spatial resolution to another, say from 20 to 10 or 10 to 20. There are a number of methods to resample the bands of Sentinel-2A MSI imagery, such as nearest neighbor, bilinear interpolation, and cubic convolution. And it's good to be mindful that resampling always involves data loss and should be used judiciously. How do we get vegetation height information from remote sensing? Sean, you may want to take that, or?
Yeah, sure. Thank you so much, Amita. And again, we do apologize for the technical issues, everybody. Thank you for your patience. And again, I think that Natasha added a link to all of the presentation slides in the window. So please do access the slides there. And all of the code that was demonstrated today is also, you have access to that code within those slides. So if you, again, we do apologize for the lack of the completion to that demonstration, but again, all of the code you do have access to, and we will have a video for an edited video that will not have any of the technical difficulties. We will have this for you within the next couple of days. So again, thank you everybody for your patience. But the answer to question 2, how do we get vegetation height information for remote sensing? There are a number of different missions, NASA missions, as well as other international space agencies. Some of these are aerial-based platforms, so they're flown on planes. Some of them are space-based, and we've just listed a few of them here For example, there are some airborne LiDAR instruments on planes. They provide three-dimensional point clouds, and you can use different software and different algorithms, both in Python as also in different GIS platforms, and these can be converted into digital terrain models, which will provide vegetation height, if that is something of interest, it sounds like, to the person that asked this question. There's also a space-based LiDAR instrument on the International Space Station. It's called the Global Ecosystems Dynamic Investigation LiDAR, or GEDI, and this provides for vegetation height, but this is at coarser spatial resolution than field scale. So this is more 250, 500 meter, etc. But it is still useful if you're calculating, say, more forest stand height. That might be of interest for your analysis. And there are also a number of ways to use L-band synthetic aperture radar, or SAR data, to calculate vegetation height. A lot of the studies that have done this have used the ALOS-2 data. This was a joint mission between JAXA, the Japanese Space Agency, and NASA. And then also NASA will be launching next year another L-band mission, an L-band SAR instrument, and this will be on the NISAR mission, or NISAR, depending on how one pronounces it. This will be launching next year. So if this is an application of interest to the community, definitely I would say refer to the methods that have been developed using the ALOS-2 data, and then they will be applicable to the upcoming NISAR mission. And for those that are interested in this application of using SAR data to calculate vegetation height, we have provided a link to a resource. This is provided by ARSET's sister capacity building program, Surveyor, and they have created a SAR handbook, which you can use as a reference. And they actually, one of the chapters is specific to calculating vegetation height from the ALOS-2 data. So we do reference that for your own interest, and I will hand it back to Amita. Thank you.
Okay.
Okay, question number 3. What do negative values of the NDVI mean in theory? So good question, and there's a lot of literature on this. So if the user wants to do some literature review, there's definitely a lot of hits on the internet that you can get. But basically, it's the difference between near-infrared and red reflectance. And so if it's negative, that means that the near-infrared is less than the red spectrum, and so the absorption of near-infrared wavelength is less in red wavelength, and when vegetation is dry. And this can be a feature of dry or less green vegetation. And very specifically, negative values can be highly indicative if you have any water bodies, so any lakes, ponds, rivers, etc. Those are definitely going to turn up as negative values when you create this index. And also clouds can also appear negative as well, just due to the spectral reflectances between the near-infrared and red bands. So those are really probably going to stand out pretty contrastly when you do this index on any given area of interest. Moving on to question number 4. Sometimes data isn't available in the Earth Engine catalog. For example, for some areas, Sentinel-2 data isn't available for more than 15 days, although the temporal resolution of Sentinel-2 is much lesser. That is correct. Sentinel-2, typically you can get it within a week because there are 2 different Sentinels, at least there were until one stopped working, which provided a high temporal resolution. And so this user is asking, why is this? Why is the Earth Engine catalog not providing all the Sentinel-2 data? This could be due to orbital gaps. Sometimes there are just data gaps in these missions, and once they correct whatever the error is, then they can start downlinking more of that data. But sometimes there are gaps in the time series of that data. So if you see any missing data, it could be a data outage for some reason. And we've also provided a link to the newsfeed on the Copernicus Sci-Hub. Copernicus is the one that serves up all the different from Sentinel-1 through 5. And so if you are noticing any recent gaps in the data, please go to the newsfeed, and there will be notifications for all the data gaps on that link that we've provided. So we do hope you will use that as a resource. Question number 5. May I ask for a preference point of view? Some variables were named first last, so that's lowercase f first, and then uppercase L last. And others were named, and it was both caps on the first and last letter of first and last. I know it is not a catastrophic question, but I may know the developer's preferences in variable naming. So this is such a good question. I've had many, I can't say philosophical conversations about this, but it's definitely been a point of conversation for myself and colleagues and friends, et cetera, on proper or appropriate practices or best practices in naming conventions. So it really is a matter of style. The most important thing when you do go about this is to apply logic to whatever variable that you are defining and naming. That's probably the most important in terms of tiers of importance. And again, this is all my opinion, so take that as it will. But absolutely, logic is the most important when applying to picking certain variable names. And then after that, it's really a preference. And whatever preference that you choose, make sure that you try to stay consistent as you go throughout the script. That just makes it more intuitive and easy to read, and it has a nice flow to it. So I think consistency, but most important, applying logic. So if you're naming, soil moisture, surface anomalies, you might want to give it some type of name that indicates that it is such, and you wouldn't want to call it some abstract name that is completely irrelevant to anything related to soil moisture, et cetera. So I think applying logic and then being consistent in your naming convention are probably the most, in my opinion, the most important. But there's certainly a lot of forums out there, and I'm sure if you wanted to go down the rabbit hole of what other people's opinions are, you certainly can, because I think a lot of people probably do have opinions on this. So question number 6, how can these remote sensing data be used to develop a regression model to predict forest fires due to climate change? And I believe, Amita, you might have added this answer. Did you want to unmute?
Yeah, so if I understand correctly, what you're asking is how do you define some kind of relationship between, say, number or intensity of fires and other parameters, either from remote sensing or, so in this case, the indicators that we showed or that Sean was demonstrating, you can construct those based on remote sensing or reanalysis model like Mehta or climate model, and in your region, and try and regress with fire number, fire frequency, fire area, fire intensity, and so that is the way to do, is look at the past data and derive the relationship, and then you can apply those coefficients that you use with climate model prediction or projection, if you like. But I think important thing is to look at past data, and for that case, in that case, like Mehta 2 model data can be used, Lancet and MODIS can be used to derive the regression relationship.
Great, wonderful. Thank you, Amita. And moving on, for the sake of time, question number 7 asks, are there VIIRS products to make vegetation anomalies? VIIRS, of course, is an instrument being flown on both NASA platforms as well as NOAA platforms. That is another US agency. And so, yes, there are VIIRS vegetation indices provided as products, derived products from these different missions on both NASA and NOAA spacecraft. And some of them we provide a link to are provided from the VIIRS NASA land team. These are both 500 meter and 1 kilometer spatial resolution. And so we provided a link for the person that asked that question below. So we do hope they will use that as a reference. Question number 8 is referring to the watershed, the subbasin levels, and the difference between, say, a level 7 and level 9 subbasin. And how do you choose? I guess I would read into that by saying, how do you choose for the specific analysis that this user is trying to conduct? First, I'll answer generally by saying the hydrosheds provides polygons, and these are derived products from an SRTM, the Shuttle Radar Topography mission, and these are derived subbasins from that mission that NASA flew back in 2001, 2002 to derive a global elevation model. And so these are based on 15 arc-second, approximately 500 meter at the equator resolution raster data. And these watersheds range from very coarse, so level 1 is basically the world, so it's probably not that helpful, to level 12, which is very detailed subbasins, nested subbasins, and this is at the finest scale, using fast adder codes. And for more information on the technical document on how this product was generated, we've provided this link below. But getting specifically to the question, I would say because these are nested subbasins, it really depends on the area of interest in which you want to conduct your analysis. So you might find that one subbasin is more appropriate for your level of analysis versus another. And that's really going to be, it's really going to be based on your interest in the investigation in which you're conducting. So I would definitely explore these different subbasins, especially in your area of interest, and especially with the say if it's an extent of a fire, that subbasin might have extended over multiple subbasins, and maybe it makes more sense to aggregate that into a larger subbasin, or it might make sense to break those up into smaller subbasins, basing on the impact to livelihood and livestock and economy and life, etc. So there is some level of subjectivity based on the analysis that person is conducting. So I would say explore the different subbasins and see what one is appropriate. We provided in the demonstration these two different levels just so you could see for yourself and have them as a demonstration. But certainly as you conduct your own level analysis, it would be highly appropriate for you to select the one that is the best for that. And we are now over time. I guess we can get through maybe one or two more questions, but I think we will be wrapping up soon. So jumping to question 10, a lot of the sensors have a spatial resolution of greater than 30 meters. How accurate are these techniques for monitoring fires at smaller scales? So I see that Amita is answering this, so I will stop and let her.
Let me just, this is a good question. You are limited by the resolution you use, but MODIS and VIRS both are used to detect fires are 250 meters to 375 meters resolution. So a pixel is usually, it does show effect of fire. So you can detect the fire even if it is relatively lower resolution than 30 meters. But if it is a very small fire or very short duration, low intensity, then there may be some error. But otherwise, you do see if something like wildfire or forest fire, you can see with MODIS and VIRS kind of resolution. Now, the accuracy of burnt area is, of course, a function of pixel size. So that is affected. Then you have to you're limited by the resolution, but basically you should be able to see the effect of fire on reflectances in MODIS or VIRS type of instruments, which are moderate resolution.
Great, yeah, thanks, Amita. And just to follow on what Amita was just saying, you might have, that fire might be, quite small in comparison to, say, that, 250 meter pixel of MODIS, but at the same time, you might not have that spatial granularity, but what MODIS is giving you is that temporal resolution. So, if a fire is flaring up and you need to be able to catch it as soon as possible, something like MODIS that has global coverage will be able to identify these hotspots, these different areas. So even though it might not be spreading throughout that entire pixel, maybe it's just one smaller part of that 250 by 250 meter area, at least you'll be able to detect it at a high cadence. So then when you have an overpass of, say, on a cloud-free day, some optical imagery of, Sentinel-2 or Landsat 8 or 9, then you'll be able to kind of investigate with a much higher spatial resolution. But that MODIS is really important for that temporal resolution. And that's really where fire, especially wildfires, because they can pop up at any given time, are so important to have that high temporal resolution to be able to identify in real time or near real time where those fires are occurring. But I do want to say that we are 6 minutes over. I want to thank everybody for sticking around. We want to apologize again for the technical issues that we experienced, but we will have all the presentation is currently available on the ARSET website, and a video, an unedited video with all of the undropped part of the demonstration that you might have missed will be available within 24 to 48 hours. So we do apologize for that again. And as well as all the different questions, we know that we did not get to all the questions today, but we will be answering all of them. And by next week, we will have all of the answers posted as a PDF on the training page. So please do, for those that did not get their question answered, again, we just ran out of time, but we will be answering them, and we will be cleaning up this document and posting it within the week. So as we wrap up, I do want to just give Amita any last words if she had any final comments for our participants.
No, I think if you find just the question 15, I think quickly it says, can we use the script to assess the fire risk for any region around the world? So wherever the data are, yes, and GEE would allow you to do that. In fact, in the demonstration, you have a section where Sean is showing how to modify this script to use it for your own region and or your own time, and you can try that.
Great, thank you, Amita. And again, we want to thank all the participants. Thank you so much, wherever you're joining from. We do hope you'll join us for next Tuesday when we have part 2 of the training. We do hope you'll join us all at the same time next Tuesday for that. And I also want to thank all of the ARSET team that has been working in the background to make this training a success. Big thanks to Dr. Amita Mehta, but also want to thank colleagues Brock Blevins, Jonathan O'Brien, Natasha Johnson-Griffin, Sarah Cutshall, Selwyn Hudson-O'Doy, Brittany Beaudry, and Juan Torres-Perez. Thank you all for all the work that you've been contributing to this training. I hope you all have a wonderful day, and we look forward to seeing you on Tuesday. Thank you.